sklearn pipeline. Description: a scikit-learn pipeline is a powerful tool for streamlining and automating machine learning workflows. It allows you to chain multiple data transformations and machine learning models together, effectively building a complete end-to-end solution. Pipelines ensure consistent data processing, reduce code redundancy, and simplify model management. Inputs: data, the raw data that the pipeline will process. It can be any format that the chosen transformer can handle, typically a pandas data frame or a NumPy array. Target: optional, the target variable for supervised learning tasks, if applicable. This can be a separate column in the input data or a separate array. Outputs: trained model, the pipeline returns a trained machine learning model after fitting it to the data. Predictions: after fitting, the pipeline can be used to generate predictions on new data. Steps: transformers, these are functions that modify the input data, such as scaling, feature engineering, imputation, or dimensionality reduction. Each transformer operates on the data in a sequential manner, with the output of one transformer serving as the input to the next. Estimator: this is the core machine learning model, e.g., linear regression, random forest that learns from the transformed data and makes predictions. Metrics: accuracy evaluates the model's ability to correctly classify instances suitable for classification problems. Precision measures the proportion of correctly predicted positive instances out of all predicted positive instances. Useful when minimizing false positives is crucial. Recall calculates the proportion of correctly predicted positive instances out of all actual positive instances. Important when minimizing false negatives is key. F1 score harmonically averages precision and recall, providing a balanced metric for situations where both are important. Mean squared error MSE quantifies the average squared difference between predicted and actual values, primarily used for regression problems. R squared measures the proportion of variance in the target variable explained by the model. A higher value indicates a better fit. Visualization plots. Confusion matrix visualizes the classification results, displaying the number of correctly and incorrectly classified instances for each class. Useful for analyzing model performance in multi-class problems. ROC curve plots the true positive rate against the false positive rate at different classification thresholds. Helps assess the trade-off between sensitivity and specificity. Precision recall curve shows the relationship between precision and recall at various classification thresholds. Useful for situations where class imbalance exists. Feature importance depicts the relative importance of different features in the models. Predictions. This helps understand which variables contribute most to the model's output. Fine-tune parameters. Hyperparameters of transformers, these control the behavior of individual transformers within a pipeline, e.g., scaling parameters, dimensionality reduction thresholds. Hyperparameters of estimator, these tune the core machine learning model's behavior, e.g., number of trees in a random forest, regularization strength in a linear regression. Uncertainty methods. Confidence intervals provide a range of values around a predicted value, indicating the level of uncertainty associated with the prediction. Prediction probabilities for classification models. These probabilities represent the model's confidence in each class assignment. Bayesian models, models that incorporate uncertainty directly into their predictions, allowing for more nuanced interpretations of results. Challenges and fixes. Challenge 1. Data leakage occurs when information from the target variable unintentionally leaks into the features used for training, leading to overly optimistic performance evaluation. Sample use case that resulted in challenge 1 using a feature that directly depends on the target variable during training. For example, using average price of a house as a feature when trying to predict its individual price. Fixes to challenge 1. Careful feature selection. Ensure that features are independent of the target variable. Avoiding any indirect leakage. Data splitting. Always split the data into training and testing sets before fitting the pipeline. Feature engineering. Create features that are independent of the target variable, removing any potential leakage. Challenge 2. Overfitting. A model learns the training data too well, resulting in poor generalization to unseen data. Sample use case that resulted in challenge 2. A complex model with many parameters trained on a small dataset. Fixes to challenge 2. Regularization. Add penalties to the model's complexity, preventing it from fitting the noise in the training data. Cross-validation. Divide the data into multiple folds. Train on different combinations of folds, and evaluate on the remaining fold. This helps assess the model's generalization performance. Early stopping. Monitor the model's performance on a validation set during training and stop training when performance starts to deteriorate. Challenge 3. Data imbalance occurs when the classes in the target variable are not represented equally. This can lead to biased models that favor the majority class. Sample use case that resulted in challenge 2. A classification task with a large number of instances belonging to one class and only a few instances belonging to other classes. Fixes to challenge 2. Oversampling duplicate instances from the minority class to create a more balanced dataset. Undersampling. Remove instances from the majority class to balance the dataset. Weighted sampling. Assign different weights to instances based on their class to compensate for class imbalance during training. Challenge 4. Missing values. Data often contains missing values, which can affect model performance. Sample use case that resulted in challenge 2. A dataset where certain features have missing values, leading to errors during model fitting. Fixes to challenge 2. Imputation. Fill in missing values with reasonable estimates based on the available data. Feature engineering. Create new features that are less prone to missing values. Model selection. Choose a model that is robust to missing values, such as a decision tree or a random forest.